Good evening, everyone, and welcome to 38th session of S.Eng training series. And today we have with us Dr. Mogadam. He's a professor in International Institute of Earthquake Engineering and Seismology, and he will be going over the first lecture on existing buildings. He will discuss some basic concepts regarding to that. With this, I will transfer the mic to Professor Mogadam.
Thank you very much. Hello, dear colleagues. I hope you can hear the voice clearly. As mentioned by Mr. Rudra, my name is Mogadam, and seismic evaluation and retrofitting has been for years my main area of both research and professional work. I'm fortunate that it is a couple of years that I have the opportunity of being involved in a special project, as they call it, urban resilience project. The name shows the importance, especially when it focuses on a mega city like Dhaka. In general, in brief, they call it URP Rajuk part. I should thank Dr. Ghosh, Dr. Ravi, Mr. Hilali, General Ali Khan, Mr. Shahid Alam, and our colleagues in S8 component of this project for organizing these short courses. I should also thank Mr. Rudra for his nice coordinations. Finally, I should thank our dear colleagues in Engineering Staff College of Bangladesh for hosting this program. The subject, as you can see, the title is about existing buildings. There are many reasons that we should pay attention to existing buildings. The importance of the existing buildings is obvious. For example, according to the literature, if we want to increase the seismic resiliency in a city or mega city like Dhaka, the most unique, effective disaster management component and plan is to retrofit vulnerable buildings, because the collapse of the buildings is the main source of both safety and fatal problems for people and from the financial point of view. Also from other aspects, such as asset management, which is very important. We should keep the investment asset that we have. From the asset management point of view, again, evaluation, improvement of the seismic behavior of existing buildings are very important, because a large amount of wealth and investment of any country is in the buildings, their buildings. It is, and it is not possible really that after, for example, publication of a new building code, we demolish all the existing buildings, because according to the new code, they have some deficiencies, and reconstruct them. So even we assume that all buildings are exactly designed and built according to the previous code, again, they are all deficient in some senses. And it is not possible to demolish all these. So we should have some plan for them. I can go on, and there is a long list of the reasons that we need to evaluate and retrofit existing buildings. So in short, I assume we agree that the title of existing building is important, that it is nice that our colleagues, they put it in the program. okay, if we accept that, existing buildings are very important. But the main point in this first session, which is on the basic concepts, the first focus will be, I will try to market this course. Because yes, existing buildings are very important. But do we really need a course on the structure, especially for structural engineers? You are all experts. So do you really need any course for existing buildings? And that's the main topic of our today's discussion, because then it will lead us to a couple points that in the next session on the linear analysis methods, the session after that on Tuesday on the nonlinear approaches, and finally next Saturday on the some important aspects of the approach. We need these items. So today, from this review, that is it needed for that we have extra course on existing buildings, especially from other point of view, you have a lots of training courses. You know BNBC very well, and even in this current program, almost all aspects of design, buildings, other structures like bridges, are comprehensively covered. So I assume you knew and reviewed techniques about design of complex and modern new buildings. So for you experts that you know everything about designing complex modern buildings, so it seems really like a wasting time. I am wasting your time, that taking your time about evaluation technique for existing old deficient buildings. So again, yes, existing buildings are important, but can't you handle them with your current knowledge? And instead of having this course late today, it's better to leave you to have some rest and be prepared for the more important subjects. Therefore, in this first session, I will try my best to say that, no, please, this course is also important. And then if we reach to that point and the items that is really differentiate between design of a new building and evaluating an existing buildings, then we will use those items to go through the methodologies. Therefore, today, in the remaining time, I mainly focus on the showing that is to trying to answer that can we just use the BNBC articles related to the new buildings and go and model existing buildings and check it if it is deficient, then add some elements or enhance some of the existing elements and come up with the less vulnerable building. Is it possible or not? There are some problems there. Okay. I should change this. Okay. Therefore, in summary, for today's course, most of our time, directly or indirectly, we'll try to focus on the first item. Why seismic design codes cannot be used for assessment of existing buildings, or when they cannot be used, because sometimes they can. Then some of the components of the assessment, like performance objectives, like the classification of the elements, or the, to better, more precisely saying, the response parameters in the elements to force control and deformation control parameter. Uh, some concepts like primary, secondary element, and the most important subject that we will talk about that today, also tomorrow, also Tuesday, also next Saturday, is the acceptance criteria. Very important and a big contribution to the evaluation of the existing buildings in the last decade. And general steps that we should follow to evaluate existing buildings. Nice. I'm first of all, again, I'm sorry that I will spend some of your time on the material that all of you know. But as I said, it is very critical for us to find where exactly seismic design is separating from seismic evaluation. And then based on that, we can make our methodology for the evaluation and later for the retrofitting. So if we look at the procedure for design of a building, what that means for us, or what we do in designing building, usually there are many elements in a building. We classify those members to load-bearing elements. Some of the load-bearing elements carry the gravity loads, vertical loads, some lateral loads. So these are the main point for us in design, designing these load-carrying elements. Also, there are other elements in the building that we don't want them, we don't really depend on them to carry the vertical or lateral load of the building. Just they can carry the vertical and lateral load of themselves and be anchored is good enough for us. So then in the design, mainly we are look at the load-bearing elements. That's our main duty. And when we say design or evaluation, mainly two concepts are important: demand and capacity. Demand is the results from the loading on the building. So we should somehow have the capability of the estimating the effect of loads on the elements. We call that in generic, we call that demands. And then we should design and assign capacities in the elements that they can withstand that demand. So design is the trying to evaluate demand and then assign enough capacity to take care of that demand. In our course, really the most important part is the demand. I will explain it again later, but for capacity, as we will see, there is not that much discussion in our course. is the same, almost the same, that we, for a concrete element, for a steel element, for the new building, how we calculate the capacities for the shear, for bending moment, for torsion, for axial load. The way that we say that this concrete element, how much capacity, axial capacity has, is not that different in our study and in the designing a new. Mainly our discussion will be on the uh, demand part, how to calculate the demands. So loads on, when we put the loads on the buildings, such as this building that this designer is trying to design, then we have some response parameters in elements. And mainly those load-bearing elements. For example, assume one of these beams. In the beam, as I mentioned, there is bending moment, shear, axial force, torsion. So from the demand point of view, we need to have estimation and based on the applied load, what is the response in the element, how much shear, how much axial load, and then trying to design. Okay, so what is the next step that usually we do in the building? More carefully, I could write building structural design. Building structural design, what would be the steps? Okay. Uh, Assuming the case of BMBC, what is the approach? What we expect from the codes like BMBC, that they somehow they have some part on loading. So in the BMBC, we have the loads in chapter 2. Chapter 2 is the loads. And then in the article 2.7, we have the combination of the loads. So everything is very clear. And we have the load that we should consider, dead load, live load, snow, wind, earthquake, all the loads are explained, and also the combinations that should be taken care of when we want to estimate the response parameters. So there are usually a specific code for loading that gives out the loads and the load combination. Then for each element, and in each element for each response parameters, usually we try to estimate the maximum value to have the demand part. So we have an estimation of the demand for each response parameter in each element. Then sometimes many clicks needed to go. Okay. Therefore, now that we have calculated the demands, now we want to design. What exactly we design? When we say design this building, what is the design? What item that we are designing? As I mentioned, for that specific beams, in that specific beam, there are different response parameters. For example, and different force deformation. For example, for the axial load, for the shear in the beam, for the bending moment, for torsions, we have the values of the load. the behavior that we want from the each of these response parameters in building a structural design. I emphasize building a structural design because later I want to go through building size. But in the building a structural design, we want the behavior of all the elements remain in the elastic linear stage. Because of that, you can see that force deformation relationship for axial, for shear, for moment, for the torsion, all in the linear range of behavior is drawn in the figures. And from these figures, that vertical axis is force and horizontal axis is deformation. Two items are important. One is the slope of each of them, which we call it a stiffness. So what is the axial stiffness? What is the shear stiffness? What is the strength? What is the moment stiffness? What is the torsion stiffness? So is that the item that we design for? Not usually. The item that we design is on the vertical axis, the strength. So when we say that we want to design, really we design mainly for the strength. And we will check the stiffness. Because if we look at one of these graphs, for example, the first one in the bottom left, for the axial load versus the axial deformation, sometimes we say that this element is flexible in the axial load when the stiffness is low. Sometimes we say it's very stiff or rigid even when the slope is higher. So the slope is important for us because if the slope is less under the same load, we will have more deformation, and more deformation sometimes is annoying. Of course, we will put some limits on the stiffnesses. But what we are designing is for strength. We don't want none of these response parameters to pass the limit for the elastic linear behavior. Because we want, when people go to this building under their weight as a part of, for example, live load, the building gets some deformation. But if they come out, it returns to its original situation. So we don't accept damage in the building structural design. Therefore, to be sure that it behaves without damage, we try to find that how much strength is needed for each of the response parameters, and then we will design. So we have one code for loading, and then we have a steel code, concrete code, and all the items in the steel code, concrete code are strength design items, requirements. All the requirements in the steel design is designed for strength. There is a chapter that how you design a element to have a specific capacity for the bend. In concrete code, again, we have a specific chapter that how we design a concrete element to have a specific capacity for the strength of the bending. Therefore, all our design focus on how to provide a specific strength. So to conclude this part, in building a structural design, we design for strength or we design for force because it's vertical axis. And as we can see, for example, in BMBC, chapter 6, it says strength design of reinforced concrete structures. So it clearly says that all the articles here is give you the approach that how you can design an element to have a specific strength on vertical axis. Therefore, the load that causes this demand is not important. So in the steel code, in the concrete code, in the chapter on design for strength, we don't say that if the is under vertical is under, for example, dead load, under live load, whatever load that causes this much demand, we should provide the enough strength that increases that demand. So our design for the buildings that don't get damaged is designed for strength, designed for force. Our design approach is force-based design. We design for force. All the articles are these articles is for designing the strength of the elements. Of course, as I mentioned, we design for strength and then check for stiffness. So it's in very short statement for ordinary loads. For ordinary loads, we expect the building before loading and after loading remain the same. Because the designer calculate the demands in all elements very precisely, and then we have good codes that for each element, each response parameter in that element can be designed such a way that the capacity, the strength of the response parameter be more than the applied. So in all the design codes, again, emphasizing that is strength-based design. Okay. But if I can go to the next page. How about not ordinary, extraordinary laws? It depends. Some of the extraordinary laws is not that big. They are not that large. So it works for the other loading that not always apply to the building. Every now and then they are applying to the building. Every now and then there is some wind and the amount of wind is not that much. So it's better to again design the building such a way that it doesn't get damaged. But there are many extraordinary loads that if we want to design a building that doesn't get any damage under those loads, really the design becomes very uneconomical. Again, depend on the region, because if you are designing for the earthquake, in some locations there are not that much earthquakes, or if that happens, the intensity is small, so it's worth that even for the earthquake we try to design them to remain linear elastic. But in many cases it is very costly. Uh, so in ordinary design, we design for service loads, then we design for loads that most of the time is expected to apply to the building. On the load, the building gets some deformation, but we expect that after removing the load, everything should return to its initial stage, no damage. Therefore, for the ordinary design, everything is so nice, so simple behavior, linear, elastic. But when we are unfortunately have to accept damage, everything becomes very complex. And some of this complexity causes problem for the existing buildings that we try to review and reach to that point. So again, for the extraordinary load, like such as blast, such as earthquake, if the design level for earthquake, usually most of the codes around the globe assume earthquake with return period of 475 years as a base for design. So if the value of this load is, although this earthquake is not a very huge earthquake, 500 return period for earthquake is not that much. We can design for earthquake that with a return period of 2,000 years, 5,000 years, because much larger earthquake. But even for that 475-year return period, that is the base of our design code. Again, the value of the force usually is not comparable but with other loads. So it is not really advisable, it's not financially possible to design the elements that remain elastic after this much loading. And we accept. So that's a very sad news that we are, as a designer, we design for damage. When we, as a, in the design, building a structural design, we were happy because we wanted to design for a structure, for a building, that there won't be any damage. If there are some errors in the estimation of loads, there will be in the next edition of code that will be modified. But the intention is not that your building get damaged. But in the seismic design, we intentionally design the building to get damaged. It's a big difference. So we design for damage. In the structural design, we design for to be without any damage. In seismic design, we know that this new building, that if it we design it according to all the items of code, and if the supervision during construction is perfect, in the earthquakes near to the level of design level, it will get much damages. Therefore, there is a big shift. Now we want to design the buildings that have a very complex behavior. They get damaged. The behavior is not linear elastic. They get plastic deformations. So everything from the analytical, from modeling part becomes very complex. Now, the main point for our discussion is why then it's such a complex behavior is not reflected in our work. As a designer, we are designing for earthquake, such simple, no problem. Still, we are using our linear elastic modeling and software, and there is no problem. How we could manage to hide all these complexities? We should have model this building in a special software that can take care of the damages, changes the stiffness matrices, redistribute the load each step to the next step, and show us the complex behaviors. But we use a simple linear software. Once it calculates the stiffness matrix, and that stiffness matrix is used to distribute the loads between elements from beginning to end. So what is, how we can do that? And the main point for our discussion is this part, because for the new building, we are doing something that we can do for the existing buildings. And because of that, we need to have some discussion today, some discussion tomorrow, some discussion Tuesday, some discussion next Saturday. So what is that point again? So before I go to the next slide, for the structural design, our intention is clear. Design a building that in the all load combinations, all elements remain without damage. It's very clear. But in the seismic design, what is the intention? Design a building that on the design level earthquake keeps its integrity and stability. Like the right situation, it is stable. The integrity of the load-bearing elements, it remains. Most probably, we can't keep it. Most probably, it doesn't worth to retrofit that. We should demolish that for the earthquake, after earthquake. So, but we design for this. We designing to just keep its stability and integrity, and even after the earthquake around the design level, it get damaged, and but people don't get that much hurt in the building, and then after the earthquake, we have to demolish the buildings. So we are designing them for the damage. And to be sure that these are referenced in the, I know that you had courses on both the structural part design, also for the seismic, but again, because I need them later, as talked before, we have in chapter 6, for example, for reinforced concrete, the strength design, all the items there is for the designing under ordinary loads, the way that the building remains undamaged. But then we have article section 2.5 on earthquake loads, and then in 2.2 earthquake resistant design, and the bad news are said there. It says that the purpose of the earthquake resistant design provision in the code is to provide guidelines for design and construction of new, still you are in new structures, subjected to earthquake ground motion in order to minimize the risk to life. Minimize, not avoiding completely, that we expect in a building that doesn't get any damages. For all structure to increase the expected performance of higher occupancy structures as compared to ordinary structures and to improve the capability of essential. Just we see for some buildings, it's hopes, the code hopes that some of the buildings, just the essential buildings, function after earthquake. The hope of the code is just essential they can work. It is not economically feasible to design and construct buildings without any damage for a major earthquake. Very sad news. How we can say that to the client that I am designing your building, but don't think that it is earthquake-proof building. In the earthquake, the building hopefully doesn't hurt you, but most probably for the level of earthquake around the design level, your building will be demolished after. You should manage another. It's not for the existing building, for this new building. So the intent is therefore to allow or some of the our colleagues requesting the annotation request that I don't know what that means, that what is the consequence of that. So I decline that. But Mr. Rudra, if it is common, please give the approval to them. So to allow deformation or so look at the intent. What is our intent? Is therefore to allow inelastic deformation and structure damage. But we try to put that at preferred location in the structure without endangering structural integrity, and prevent structural collapse during major earthquake. What we expect for this new building, according to code, well designed, well constructed, well supervised, hopefully in that level of earthquake doesn't get collapsed, not damaged. Okay, so if we want to go to this kind of behavior, that some part of building get damages, some part get plastic deformation, naturally we should have a much modern and sophisticated modeling, nonlinear modeling, and then for the and the then good acceptance criteria to check that, but we don't do this. How that happens? And how the way that we do that in the new buildings, that way, why is not applicable for the existing buildings? So we should go a little ahead. So, one good thing that usually the researchers do after earthquakes, they try to, because the earthquake happens, you have the earthquake ground motion record, and sometimes you have the specifications of the buildings, so you can model that and study that what happened to this building. For example, this is from the paper in a world conference that assessing this 50-story building damage in one of the earthquakes in Chile during at the year 2010, and so a building, very nicely built building like this, after earthquake becomes this. For sure, the intent of the code is not this way. So the building in 2009, in the 2010 becomes like this, is not acceptable. if everything is according to code and this happens, and if the level of earthquake that happened is around the design level earthquake, then we should change something in our code that it doesn't happen. Because we accept damage, but we don't accept, as it's mentioned here in the BMBC, we don't accept collapse, just damages. Integrity and the also the stability should remain. So this kind of studies help us to improve the code. For example, for the buildings that they have only shear walls, maybe the level of redundancy is less, or some for the tall shear walls, there are not sometimes not good mode of the collapse, so we should take care of them. And every time that something like this happens, this kind of studies give us some clue. If it is a more redundant structure system like structural frame systems, then again, there are sometimes have excess displacement. So there are many items in the codes, both from the structural point of view. For example, from a structural point of view, shear wall for taller buildings have some deficiency because the shear wall have a bending behavior. But frame can have a shear behavior with less deformation. That's from a structural point of view. Then from the earthquake point of view, there are some points that if we have a couple building, both shear wall and frame, because we use them in the elastic software and elastic software, linear software, can take care of the order of damages. Therefore, we have some articles that, for example, 15% of load should be bear by a shear wall alone and 25% by the frame alone. These kind of articles try to solve the deficiency of our model. But the main point is this is not the behavior that we accept for the buildings. When we say that we accept damage, we don't accept this kind of damages. Another example. For example, here, again, these are not according to the code. Or if it is shown that they really designed them for according to code and this happened, again, then we look at the level of earthquake. If the level of earthquake is around the design level and this happens, then our design articles and approach and requirements are need some modification. We don't accept. Code doesn't, when it says this damage, again, not losing stability, losing integrity. Here, for example, in the bottom picture, the middle part, that somehow the irregularity was more compared to the other part, get most of the damages. So we don't expect this much of damage. It is not according to code, and if it is, the code needs change in the requirement. This one is also not the way that we expect, we accept as a intention of the code. That, for example, the building before the earthquake, in the ground floor has a floor, but after the earthquake, the ground floor is gone. So, as you know, the soft story, the weak story, soft related to the stiffness, and weak related to the strength. on the vertical axis. Weak story, the story that is has less strength, and the soft story is the one that the slope of the load deformation for the story is low. So usually in the previous versions of code, we didn't, the penalty for irregularity was only change of the method of modeling and analysis. Therefore, if you had a building that has some kind of irregularity, previous codes let you that is no problem. You can go ahead, but you should use more sophisticated analytical methods. Instead of, for example, static analysis, you should do, for example, the response spectrum analysis, dynamic analysis. But they don't limit you. They don't forbid you to design a building with irregularity. But this kind of damages, weak story, is so, the consequence are so huge that in most of the building codes, seismic building codes, now they have severe limitation for the buildings with the weak story. And in the programs for reducing the vulnerability in cities, for example, in California, they have two very good programs. One is related to the recognizing and curing the buildings with the soft story, and the other one is for the old reinforced concrete buildings. Anyhow, this kind of damage, again, is not according to code. We don't accept this, and code doesn't want, the intention is not like that. If this is designed with code, and it does happen, it was not the intention, and they should modify the code provisions. But these are according to the building is get damaged. There are lots of damages in the elements, and most probably this building will be demolished after this earthquake. This one maybe can be taken care of with some retrofitting, but anyhow, this is the buildings that we, as a expert, as a structural expert, give to our clients. And after this earthquake, they don't believe us that we design according to code, but because they thought that if your building is the new building according to new code, shouldn't get damaged. But really, we are designing for damage. The way that we design, we expect this kind of damages. So, okay, very good. Now, how we can handle that in the new code, this kind of a very complex behavior, how we can handle that in our design for the new buildings, then we can use the same approach for existing buildings. So there is no need really to extra approach, extra code, extra course. What is the problem? Where is the problem? We should try to find the problem. So again, the main question is, can we use the seismic design approach of BMBC for assessment of an existing buildings? We are using this approach, very nice, very up-to-date code for the new buildings in the left. For the new buildings, we model, we check the stress ratios. If there is a problem, we change the property of the element, solve it, and then we get the final design. no big deal, no much complicated stuff needed. And we are using such an advanced seismic design, for, especially for these new complex buildings. Then for existing buildings, for old ones, for these ones, they should be much simpler. We shouldn't make it more complicated. But why is it like this that we make it so complicated for existing buildings, which are much generally simpler, older buildings compared to these new, complex, up-to-date buildings? Therefore, we should, BMBC, I wrote NBCC. So BMBC, seismic design for assessment of a building, how it works, uh, how we design such a complex behavior for this building, for example, lots of damages and in different points, but it has a stable situation and integrity almost is remain. So how we do that? How which complex software we use to handle this kind of behavior? Where we look at the inelastic deformation, how we check if this inelastic deformation, which means damages, if these damages are endangering structural integrity or not. Where during design, I can't see any location that we really model, check any damages, level of damage. No, everything was so simple, calculating a base shear, distributing along a height, and find using elastic model and software, calculate the response parameters in the elements, and then we have it, go to the code, design that the strength be more than the demand. So where are these complex behavior that I have shown down there, where we look at them? For, what in the article in the BMBC says, they said to allow inelastic deformation. So for the moment, for the shear in that specific beam, it says that we accept damage. But this damage shouldn't endanger structural integrity and to prevent structural collapse. So what this means, when this happens, when this building will get collapsed, if we look at the cases for the moment and shear there, after elastic range and going to damages, we can see different behaviors, and these different behaviors can have the effect of stability or instability. There is a concept that everybody of us have heard that many times. We say we handle the inelastic deformation by ductility, by providing ductility. So the structural design is designed for strength, is designed for force. The seismic design is designed for damage, is designed for ductility. That is designed for strength. This is designed for damage, designed for ductility. What is the ductility? Well, the ductility, as you know, that after this point, what happens after this point? What happens after getting the element or the system? It becomes a mechanism. The stiffness becomes zero or near zero. What happens? If that element, if that system get some plastic deformation, but doesn't lose the strength, we say that we provide the ductile behavior. In general, it's not possible that it doesn't get any lose in strength. When the lose of strength becomes almost 20% of the maximum strength, we say that the ductility capacity should be calculated at this point. And after this point, we assume that it failed. So failure and the losing integrity for us means that if the response parameter passes that level of ductility, passes not the level of strength anymore. We don't design for strength, we design for ductility. So what if we think with this approach, what should we do? We should model the building and impose the earthquake to it. The building gets damages. We should monitor each element and in each element, each response parameters, and see that if they can, if none of them passes the ductility capacity of that element. So, for example, in reinforced concrete element, some behaviors, shear, for example, is very difficult to make it ductile. So we assume that is not ductile. And later, for these parameters, in the existing buildings, we give a name. We say these are the deformation control parameters. But for example, moment is a deformation control. That one is a force control. Sorry, force control parameter. This is a deformation control parameters. But anyhow, see, if we want to design a new building for the earthquake, we should do nonlinear analysis, and for each response parameters, see how much damage they get and is it acceptable or not. But we don't do that. How we can do that? Without doing that, how we design for earthquake? So that's the main point. That's the main parameter that we should look more carefully to see where it causes problem when we want to apply this methodology for the existing buildings. Go to BMBC. What we do in the BMBC? In BMBC, we assume a level of earthquake, for example, a fraction of the maximum, say, earthquake comes to the acceleration, which acceleration for the earthquake with return period of 475 years, that modified by some coefficients, this acceleration multiplies by the mass. The G now is the mass, it becomes weight. But anyhow, using the second law of Newton and get the force. So everything is almost clear, very easy approach. We calculate the uh, acceleration multiplied by mass of the building, get the force that the building should withstand, and then we design that building for this. What exactly we do? We calculate the V, the base shear. We apply that in the load combination with other loads to the building. For each element, we calculate the maximum response parameter, and then we design. But when I say design, we design what? Design a strength. A strength of that for this. And that's done. Where goes that damage? Is the damage of this is good, not? First of all, why it get damaged? What in the design level earthquake? Why is get damaged? Because of this R here. Because the other parts get the estimation for the base shear. But then we design, we calculate if everything is good, if all the zoning, earthquake zoning of the BMBC is good, the formulation is good, everything is good, the level of the load is the same formula without R. So if we wanted to building to remain elastic, we should design for this formula without R. So we can use a linear elastic software such as SAP tabs, and then design for this level. When we say we accept damage, because this load usually for the buildings in earthquake-prone regions are much more than other loads due to the wind, due to the snow, due to the live and dead load. So we divided it by a number, by R. So here we accept damage. Here we impose damage. You know that the design level earthquake will impose R times this value to the building. But we design the strength, ordinary strength design for 1/4 of that load. So we accept damage. We, as a designer, are making damage to this building at the design level because we divided by. Okay, now we did good job. We reduced the strength, and now we are sure that in the design level earthquake, the building will get damaged. For sure, because our estimation is R times that will impose to the building. But we put the strength, the capacity, 1/4 of the demand. So it will get damaged. But how about looking at the level of those damages? If those damages are acceptable or not for each element, for each response parameters, see that if the level of in plastic deformation passes the ductility capacity of that or not. But usually we don't do that. How it's possible? So dangerous approach. We design a building for, say, 1/5, 1/7, 1/10 of the loading, and then we are happy that it will be won't collapse. Get damaged, but won't collapse in the. No, it's not that simple. Yes, the problem is really complex. But why we can't see the complexity? Where is the complexity? And that's the exact point that we need to review for existing buildings. That complexity, that's we hidden it somewhere in our approach. But we should find it. Where is this complexity? In fact, the complexity is very near, is not that far, is very near. And that's a traditional approach that we had in the history. Always, we have a modeling and analysis part, and then we have a design. We should model this building, analyze it under applied load, and then we should design. So the capacity be more than demand. Whenever modeling analysis is difficult, we put some requirement in the design. So we move the difficulty from analysis, from modeling to design. What that exactly means? That means that we had it, for example, in previously in some things such as P delta effect, for example. P delta effect is a nonlinear, is a second order analysis too. But we wanted to do that. We designed a building for P delta using the elastic linear soft. So what we did, for example, for reinforced concrete, we calculated the demands based on the simple modeling, simple analysis, elastic models. But during design, we multiply the moments by 2 factors, one for the P small delta and one for P big delta effects, C1 and C2, as they are famous for. So it is traditionally we do that. If it's difficult for you to model, if it's difficult for you to analyze, use some prescriptive requirement in design. And in our case, these prescriptive details are mainly those detailings. So what happens? We make this. We make the analysis simple, make the detailing advanced. Make this. So what that means? We don't, for example, if I return to, no problem, I don't return to the slide, but for example, in that slide that the building get damaged. We want to model a building for damage, and for example, in a reinforced concrete column or reinforced concrete beam that can damage in the shear, and it is very difficult to model. The interaction in a column between shear axial load and shear axial load and moment is very difficult. So what we can do? Now we expect every engineer that wants to model a building for earthquake should do such a sophisticated modeling. No. We say do simple modeling, but we put some design requirements that never this element get damaged in that mode. So we put lots of transverse reinforcement, special hooks, many things that those special, difficult to model, the mode of failure that can change our scenario can be removed. So whenever a subject is so difficult to model and analyze, we try to use some experimental, some prescriptive, some results from experience in the design, and use those detailing to take care of the complexities that we didn't see in the modeling and analysis. That's the approach here. So very nice. For VMBC, we do such advanced, difficult behavior, a building that get damaged, and each element, each response parameters passes the linear limit, but without using any difficult model. So where we hide it in the design requirement regarding ductility in design codes. As I mentioned, in design codes, they shouldn't say a section for being the section for dead load, the section for live load. No. Whatever load that produced it moment, there we have the procedure to design to reach to a specific level of the capacity for moment. But for earthquake, we have specific chapters. That specific chapters, what is the purpose of that? Covers this simplification in analysis. So all this, whatever R that you select, you pay there. Higher R means that you put less strength in the buildings, it gets more damage, you pay there more detailing requirements. So the scenario is very nice and almost working well. We hide all the complexities in design requirements. In these, for these R values, how we calculated that based on the behavior of each lateral load system. We look at that how much ductility each system has, and based on the ductility that this system can provide, then we assign a specific value for R. If a system, the capacity of ductility and damage before losing strength, before losing integrity, before losing stability is less, we use less. And if it's more, we use more. So the relation between these concepts, we design for a smaller strength that we know causes damages. We know that causes damages because we know that is R times less than level of the base shear for the design level earthquake. And a design level earthquake is just 475 years earthquake with period earthquake. It's not 100,000, 2,000, 3,000. It's just 475. So it's not a big deal. But again, even for that, we divide the base shear by R. 1/5, 1/7, 1/9, 1/10. So we reduce really drastically the amount of base shear. So we know that strength is very less than the applied load. And this get damages. Ductility is the capacity that with our design and detailing, we can make those damaged parts to behave such a way that they get damaged. The stiffness is zero is a mechanism, but it can handle some deformation, plastic deformation, without losing strength. This is the key word, without losing strength. Because if this element that is getting damaged now loses strength, then the load, diaphragm, transfer its load to this one, this loses strength, so the progressive collapse in the building happens and the building will collapse. We don't want the collapse. We accept the damages, but we want to have the damage without collapse. Therefore, when we say design for ductility, seismic design is designed for ductility. It means we design for damage. And in existing building codes, the level of damage, we call it performance level. When we say we design it for immediate occupancy, IO, we design for this level damage. Design it for LS, life safety. Design it for this level of damage, which is more than IO. Design for CP, collapse prevention. So performance levels that we see later that are different level of damages, different level of damages becomes, for example, here becomes IO, here becomes LS, here becomes CP. So the relation between ductility, damage, and performance level is they are directly connected and saying the same concept. So by assuming R in our formulation in BMBC, we accept that we need ductility, we will have damage, and the performance levels are not elastic performance level anymore. The building will get damages. And this very difficult behavior is covered by design requirements, by prescriptive design approach, and by detail. We don't see that in the model. And we will continue on this and to reach to this point that unfortunately, for the third part, unfortunately, this approach is not working for the existing. And because of that, we need this course. Therefore, if we continue, as I mentioned, vertical axis here is base shear, and the estimation of the base shear in design level earthquake by BNBC is this value. This value is the estimation of BNBC of design value. That a 475 level return period earthquake will impose this much base shear. But we can build the buildings for this much, because we see for the buildings that are in the earthquake prone zones, usually this value is too much. So it becomes like a very strong, very heavy, very costly buildings. So very easily we accept damage. By how in the calculation, we say, okay, put for this level, strength this much, or this much, for R1 or R2. But we know the consequences. If you design it for R1, you should provide this much ductility capacity in the building. But if we consider that for all the cases, this is the level of deformation in buildings, which for many buildings is true, then if you design For R2, you should pay it by much more detailing because now the building has very small strength, very easily gets damaged. And you should provide lots of capacity in these points that get damaged. Very good detailing. It's not easy that a reinforced concrete section get damages, the reinforcement get yields, and it increases, there is cracks, and then keep the strength still, this stiffness is zero. Is so much damage that the stiffness is zero, but still keep that level of loading that it was handling before. It's lots of detail. So for the new buildings, we have lots of detailing requirements and we can apply them. You can go to the site, the construction site. When you saw that this column doesn't have the detailing requirement, you say demolish that. Our binary approach, 1 or 0, should be exactly like detailing. Not demolish that. And that's the problem with existing buildings. We can't do that. If we go to an existing building, none of the elements have the requirements of code. Demolish this, demolish this, demolish this, demolish. We should demolish the city. It's not possible. Unfortunately, it's not possible. We need this course because there we didn't go through difficulty. We provide detailings that keep us out of the difficulties. All those non-linear behavior here, we never see it in our design. Where are they in that requirement? Put the, for example, the transfer reinforcement this way, the length of the between reinforcement like this around column, the number of reinforcement should be like this. Many details that all those details keep the difficulty, complexity, and handle those unwanted behaviors, local, especially local behaviors that can happen and ruin our scenario. So very nice scenario. Depend on how much, with what depth you can provide the detailing, you can have larger. If you can impose this detailing in this site, you ask your designer to use a smaller rod because then you don't need that much ductility capacity. Therefore, that's the main point in our approach for the new buildings. What is this? Okay. That was in fact very good thing. So, as a sample, if we want to check where those difficulties, complexities, where they're high, yeah, in 6.1, in chapter 6 in general. No, sorry. Chapter 6 was a strength design. Where are those complexity here? 8.3. Yeah, 8.3. Earthquake resistant design provisions. Here, then you see detailings. Lots of details. That these buildings, this building with shear wall that we are designing such nicely, simple, elastic, in SAP, in ETABS, very easily. But if we expect such a complicated behavior during earthquakes, but we don't model this behavior. We just use this detailing, this provision in the we can call that ductility providing chapters. You see, here it says earthquake resistant design. The name of the loading is here. We shouldn't, in the design code, we shouldn't name the load. What is the difference? Axial load is from dead load or axial load is from the live load. We want this much, we want design this much strength. But here, we don't want the strength. We want the ductility. Therefore, for this specific loading that wants ductility, and you don't consider that, you don't check it in the design, in the modeling analysis, here, by just applying them, you get the acceptance. Therefore, to summarize the design for the new buildings, our earthquake resistant design for new buildings is two parts. One part is simple modeling and analysis. This is part one. Very easily, simple, elastic, linear. We put the load that is divided by R as a base shear and design the strengths. We know everything that we get is wrong. We know that is not the displacement here, because the real displacement is in the earthquake is more. And because of that, we always multiply the displacement that we get from SAP ETAPS based on the system that we are using. But we are putting a smaller strength in the elements. We know that it causes damage. The second part, taking care of this damage, is not in modeling analysis. We could have done. We could ask that everybody that wants to design a building for earthquake should use nonlinear analysis. Because behavior of building, the earthquake is nonlinear. Get damages. So you should model the building completely nonlinear. Check your design that none of those response parameters in none of the elements passes the ductility limit of that element. We should design like this, but we don't do that. We don't model the most difficult part of the behavior. Why? Because we have the support of those detailing. This detailing that comes from years of experience in different earthquakes and lots of observation of damages. Can you hear me? I think I lost the voice. I hope you can hear me. Can you hear me?
Yes, Dr. Mogadam, we can hear you. Hello. Hello.
I hope
Dr. Mogadam?
you have, because I lost
We can hear you, Dr. Mogadam.
my voice here on this system. Okay, assuming that it is, you have my voice, I continue, hopefully.
Dr. Mogadam, can you hear me?
That's true. Okay, so to summarize, the way that we design the building is for the uh, new buildings that we use is very easy approaches for the um, modeling and analysis. And then we have the, okay, let me, I have a message. We still have, oh, perfect. I put this here. Yeah, very nice of Mr. Rudra. Yes, please feedback me if it, because I put a system in front of me just to see if my voice was and it disconnected. Perfect. So what we can do here in the, to give the general approach, very simple. In BMBC, we estimate the base shear. For design of existing building, tomorrow we will discuss how we calculate the base shear. Much simpler than BMBC. So it's easier. It's a couple coefficients, and then again, second law of Newton, the same as here. Here, you see the coefficients seems much more difficult than here. So again, we do the same thing, calculate the base shear. But in the new buildings, in BMBs, we divide all the demand. This is demand. We put this, apply that on the building, and then we will provide the capacity to be more than this demand. But in calculating the demand, because we know that all those detailing, all those consistent detailing will be applied, then we divide it by R. So we reduce the level of earthquake applied to building for all elements at the same level. Because we know this detailing that we provided will provide a consistent ductility for the whole building. Now, returning to the question at the start of the session. We talked that it's not a big deal. Right now, there is a building here in need of evaluation. 3-story, 4-story. This is a school. And they want to add 2, for example, a story to it. Or it is old according to previous codes. We want to check. So what is the big deal? What is the big deal? We model it. We will model it and find the base shear, and then check the demands in all the elements, response parameters, and then check the existing capacity with that demand. But this is very dangerous. This is very dangerous approach that for an existing building, we use this formula. Because these are, so everything comes to one simple thing, R. Why we can't use the approach for existing building for R? This R that you put there, 5, 6, 7, is when you have all those detailing requirements. That even in new buildings, it is difficult to imply and implement. So for sure in the older buildings, they don't have. So the R value for the older buildings, if for this new building, the R is 7, for that older building is 1.75, is 1.5, is 2, is not 7. So if we, for this existing building, we use the R values for the new buildings, that is based on all, assuming that all those detailings are applied, is very dangerous. So that's not possible that we use this formula for existing, because the R value for existing buildings, we can calculate the R value for the existing building. But as I said, it becomes 1.75, becomes 2. So all the building becomes vulnerable. All the elements, all the foundation, everything. We should retrofit everything. It's very expensive. So we should change the scenario. We should have another course. So we can't just use R. We can divide all the base share for the system on R, on one R. Because either we are endangering the safety if we use R based on the new building code for the existing buildings, very dangerous. We should never do. Or use the R factor based on nonlinear modeling pushover of the building, for example, and we find the R. That R value is very, make the retrofitting very costly, because then the R value that becomes 1.75, 1.5, 2 is based on the worst element. The worst element in the each load path. Limit the R value. So then we if we want to use, if we want to divide base share of the building, elastic base share of the building by a value, if you use the one that is code, it's dangerous. It's killing people, because the real R value of this building with this much deficiency is not the same as that system based on all the requirements of detailing code. The other side, that if we use the R value for the building, the real R value of the building, it becomes very small. So the most deficient element govern on that R value. So we can see there is no R value in the code. Therefore, what in the many of the existing building codes, we have linear approach. In some of the codes for existing buildings, they say just nonlinear. Forget about the linear approach. They don't accept linear approach at all. Just the nonlinear approach. But many others, like ASC 41, very good code, accept linear approaches. But in the linear approach, you can see R value. So we don't divide the demand for the whole building by R value. We calculate the demand without any modification, apply that to the building, and then element by element, we decide that what is the R value of that element. We call it M value. What is the M value of this element? This element, oh, good detailing. The M is high, is 10. Oh, the other beam is very bad detailing. M is 2. The other one, M3. So it's very difficult. Very difficult. Time consuming. But the main purpose of the systematic retrofitting and evaluation is to be financially uh, as low as possible. Because it's really difficult to apply retrofitting to existing building. There is a hospital, they are working. This is a school, they are working. You should go restart their work. So you should reduce not only the cost of the direct material and workmanship, but also the cost of these disturbances, which is more costly than that cost. So in systematic retrofitting, everything is about the money and time. And because of that, we expect and we encourage more analytical work, element by element, element by element. But don't use the overestimation. Therefore, there is a big difference. There is a big difference between approach for new buildings and approach for the existing buildings. I should also remind that when we say evaluation of the or assessment of the existing building, it's not always a very difficult job. All of you experienced structural engineers, you know, you have lots of experiences. You just go to a building, a concrete building, a masonry building, steel buildings. You can find many deficiency and providing some detailing or advice to increase the seismic behavior of that building. It's not very. The easiest is just to trying to make reduce the weight of the building. Some of the floors, some of the slabs, some of the partitions. If you can reduce the weight, it will reduce it. So not always the evaluation and assessment of existing building should be difficult. Just for when we say the systematic way is more difficult. Otherwise, we have many methods. For example, in risk analysis, now we very easily we use fragility curve, vulnerability functions, very easily for disaster management. We calculate the number of masonry buildings in this area, and then do have a fragility curve that based on experiences, based on analytical models, it shows that under this level of earthquake, how much of them will get damage or how much of them will pass a specific performance levels. And we do calculation that this many of these buildings will get damaged, and for repairing needs this much money. Very good, very quick calculation. So if we just want to give a general view, we can use fragility curves and vulnerability functions. But then we can't say that this specific building is really this much deficient or not, just generally. We can do visual screening in a few hours by filling some forms quickly, even from outside of the building. Look at the irregularities, look at the some points that in the previous earthquakes we have seen that existence of this kind of effects can really get vulnerability of increasing vulnerability of buildings, and then we rate the building. So we have many different approaches. RVA, PA, DA, AC 41 has tier 1, 2, 3, many approaches. But the thing that we are focusing in this course on is the systematic. What is the systematic evaluation? As I mentioned, if we visit a building, we can increase, we can give some recommendation easily to uh, to improve the seismic behavior of that building. It's not difficult. But if they say uh, their demand from us, the client's demand from us is check this hospital at this specific ground motion level, can provide this specific performance level at the earthquake with the return period of 2,500 years. Can this hospital provide life safety? Then we can't just fill the form and say we should model, we should calculate the damages, we should calculate that this building can withstand that earthquake at all without failure, or if just get damage, is how much damage is there? Is this damage corresponding to IO or LS or CP? So there it should need more accurate modeling and analysis when they want us systematic evaluation. Otherwise, there are lots of, and each one of these approaches and many other approaches, all are very useful. So when we want to use the evaluation methodology for existing buildings, we should look at our problem too. What we want. As I said, sometimes for the disaster management, we just want an overview. But sometimes it's a specific building and very accurately we want the results. That's the systematic evaluation. So when I say systematic evaluation, I repeat the systematic evaluation, I mean this, that we want to check the building, the performance of the building in the different level of earthquake, and come up with the results that it can pass this requirement of that performance level. This means modeling. Therefore, when it comes to the earthquake consideration for the buildings, we have is a long history for a long time that we have codes and standards for new buildings, such as BMC. Very up to date, very good. For existing buildings, is during this 10 years, it comes to the mostly, you see, in the world becomes like a standard. Before it was pre-standard, it was some recommendation. But for buildings that experience damages, they are even more difficult to model, because from the cracks, from the residual displacements, you should for each element see that how much you should reduce the stiffness of that element, how much you should reduce the strength of that specific response parameters, how much you should reduce the ductility capacity of this element because of this damage that it is observed right now. So, and as far as I know, we don't have a standard or code for the post-earthquake damage. We have a few very good reports, but not code. So for new building, we are a history of engineering. Existing building is much newer for the systematic evaluation. For post-damage earthquake buildings, still we are a little far from the systematic approach. So for the this systematic approach, that sometimes it calls DEA, detailed engineering assessment, detailed engineering analysis, sometimes come in the ASC 41 systematic evaluation and retrofit. There are some concepts that are needed. We should consider, which we should be able to consider different level of earthquakes, and we should have different level of damage. We call them different level of performance, and we should be able that whatever they ask us, we can check. If they say check this building for this level of earthquake, for example, 100-year return period earthquake, for this level of the performance, we should be able. If they said for the much longer return period earthquake, for another level of the performance, we should be able to do that. So this performance-based evaluation is a main part of and main structure of the this approach. So generally, in the new codes like BMBC, we don't have that. Everything is set, fixed, a specific level of the earthquake and a specific level of the performance. As we read in the text of the BMBC, says that we try to design a building that doesn't cause death of the people. So it's a specific performance level. It's something between life safety and collapse prevention. And for a specific level of earthquake, for the earthquake that with return period of 475 years, or as here mentioned, 10% in 50 years, because we usually assume a building can last 50 years. So it says that there is 10% probability that this building experience larger earthquake than what we are designing. So the design level earthquake is the level of earthquake that there is 10% probability that this building experience larger earthquake that this design. 10% is too much, but that's the approach. But in the evaluation, our methodology for systematic evaluation should be such a way that every earthquake hazard level that they want and every performance level that they want, we should be able to check it. Earthquake hazard level, that which one of these we pick tomorrow in the linear analysis method will be the base shear. So tomorrow, when we discuss about the linear analysis, if they ask us check this building, evaluate this building for larger earthquake, it becomes to evaluate this building for larger base shear. So that formula that we saw, and tomorrow we will discuss, we have a formula that gives us the base shear for each level of earthquake that they ask for us to check. For the nonlinear analysis that hopefully on Tuesday we will discuss, the earthquake level becomes the target displacement. If they ask that check this building for this larger earthquake, means that push the building to larger displacement. We say 10 centimeters. A smaller earthquake, 2 centimeters. Very big earthquake, 50 centimeters. So the quantification of the earthquake hazard level will be base shear in linear analysis, will be target displacement in the nonlinear analysis. The target building performance level here. These target performance levels, these are we see a couple of them according to definition in one of the codes. But when we want to check it, how we check it? How we check it? In the linear method for the locations that the damage is accepted. Because some location, if damage happens, the building is gone. So we say, oh, force control parameter passes the limit, so it's gone. But we say, no, the deformation control parameter passes the S.Eng limit. Then we ask, oh, how much? In linear analysis, the level of this demand to capacity, this DCR, demand to capacity ratio, shows how much is damage this deformation control parameters. And we have the M factors instead of that R, element by element for each. Very nice, really enjoyable to look at these tables for each element with every kind of deficiency. We have the R value, M value, very nice. And for the nonlinear analysis, for every element, we have the tables, for each performance level, the level of the plastic deformation that is accepted. So very exciting things are expecting us for the both linear analysis and nonlinear. And in fact, all the important things are here in acceptance criteria. So we have demand, we have capacity. And in capacity, we need the calculation of capacity is according to whatever we learned till now. It's nothing new. But the limits for each performance is new here. Very nice. And most of our attention will be in calculation of demands for the. So for the different level of earthquakes, one of them, for example, let's say performance life. What is the life safety? It mentioned. You expect something like this. I will show a couple of tables too, but here is not that. That when it says life safety, what is the feeling that we can get from building? Is some residual strength and stiffness left in all stories. Gravity load bearing elements function. Very important. Our red line is gravity load bearing elements. All these damages we accept in the lateral load resistance system. Gravity load bearing elements is very dangerous because always the gravity is there. Earthquake goes, applies to the building and goes, finishes. And because of that, we accept damage. We say, just bear with earthquake. Just keep the integrity, keep the integrity, the direction of earthquake changes. Okay, we lift. But the gravity load is always there. So if the damage in the gravity load resisting system happens, it's gone. In the code, in the code for the new buildings in BMBC, in the R value tables, you can see that sometimes a building is shear wall buildings. We call it, for example, load bearing system. Sometimes is part of the, for example, a frame system. And the R value is the same thing, the shear wall, but the R value in one is more than other. Where is less when is the vertical load bearing system? Because if element uh, carry gravity loads, we don't want too much damage in that. We don't let too much damage on that. We reduce the R value for that. But it's the same element, but there is less vertical load on that. The load, vertical load is carried by other elements, we increase the R value. So it's very important that for life safety, gravity load bearing elements shouldn't be. No out of plane failure, some permanent drift, damage to partition. So give you a sense that when we say life safety, what we expect when we, after earthquake, we go to the building. But then we have specific engineering demand parameters that quantify this life safety. This is generally the overview of the damage, but then we need the quantification, and the quantification is acceptance criteria. Those acceptance criteria, such as M factor that I mentioned instead of R factor, is like that. So one important part of all this systematic existing building evaluation is discussion about performance objectives. Because otherwise, and many times, in fact, you see that the people who use a building when they want to retrofit it have a very unrealistic ideas. That behaves very well under very large earthquakes, and then that the retrofitting can be provided, but it will be very costly. So the consultant should explain that what is the consequence of selecting each performance objective. When you say that, for example, for this earthquake, I want that my building will be the immediate occupancy performance level under this. Providing this performance level under larger earthquakes will be much more difficult. The same performance. And this performance, target building performance levels, have two components. One is structural, one is non-structural. So you can see here, then we say that the immediate occupancy performance level 1B. 1 is for the structural part, immediate occupancy. So structural is 1. And B is for non-structural part. Another table will show it. So very nicely separated that what you want from the structure at the different level of earthquakes, what you want from the non-structural element from each element of earthquake. And sometimes it maybe is not recommended that, for example, you select some of them. Is not recommended, especially for non-structural element that very much happens. So when we say the structural performance level means how much damage you accept. How much damage? IO, immediate occupancy, means less damage. Life safety means more damage than immediate occupancy, but less damage than collapse prevention. So each one of these, selection of these has a cost tag and has a consequence tag that the owner, the client should look at both sides and select the most proper ones for this building. So for the building, target performance level for the building, structural parts, sample area. The same thing is here. So, structural performance level And then here, oh, okay. Here I copy paste the concepts for structural performance levels is the same table at the previous slide, but the concept that, for example, for concrete frame, when we say that collapse prevention, what that means to the primary elements for the that gets the carry the lateral for elements that just carry the gravity load from the drift point of view, what the collapse prevention means. When we say the life safety, what it means for a concrete frame, extensive damage to beams, spalling of cover and shear cracking in ductile columns. But here, in immediate occupancy, minor. But in collapse, extensive. So here, everything is very general, but then it will be quantified with the numbers in the tables, both for the linear analysis tomorrow and for the nonlinear analysis Tuesday. But here gives a sense of what it means from each performance level. How much damage we expect. And for non-structural elements, again, every version of code changes the definitions. Before, for example, it was life safety and immediate occupancy and operational. Now we don't have immediate occupancy, we call it position retention, because we usually for non-structural, for us first, it is important that they don't cause, because many of the fatalities in the earthquakes are because of failure of the, for example, infill walls. So non-structural elements, they can cause lots of problem for life safety. Then maybe we ask that these elements should be at their position, so is a higher level compared to that, and even more if we want them to can function after without much repair. So for everything, for cladding, for the chimneys, here explains that when different level of performance, what is their meaning from the state of the damage that we expect, and what is the then we will quantify them with the numbers as we can see them. So there is an important thing. As we said, there are lots and lots of approaches for the evaluation of existing buildings. There are lots of approaches. It's very simple. But when it comes to systematic evaluation, we don't want any simplification. Because simplification means overestimate. We don't want any simplification. So it's very complex. We want it to be as complex as possible. We don't want any to be simple. Because when you want to be simple, it means that these three beams, you want to approach them the same way. So you should use, you should consider the worst beam as a case for design to be safe. So it becomes costly. We don't want to. We want to divide each beam for itself. We check each beam by beam, because we don't want, if we want to use the same R for both of them, we should use the smaller. or the M factor as we call it. So generally, for systematic evaluation, don't expect to be simple. It's not like a design course. In design course, we want to be simple because a wide range of engineers should apply that, and in different areas of country, so should be simple, and we put all the complexity in the those details. But here, no. For the existing buildings, especially for the uh, systematic evaluation, there is no need that all the engineers be involved because we want to be as cost effective as possible. So should be very, very complex to use all the capacities of the building. So this, and I'll give you some samples that how it becomes. The main thing is we divide, every subject will be divided. Every subject will be divided. For all load-bearing elements, we don't use the same approach. We call some of them primary, some secondary. For primary, we all the acceptance criteria are different than secondary. Primary are those elements that we consider them that most of the lateral load will be carried by them. Secondary, those that we expect mainly the gravity loads they carry, but we don't want them to get involved in the carrying the lateral load. No, there is no time, but we have the same concept for new buildings too. When you design the building, you can, most codes let you, that you select assume that all the frames in one direction are moment resisting frames, concrete moment resisting frames. But you as a designer can assume just these two at the parameters are the lateral load resisting system, and the middle ones, for example, as a secondary, as a gravity. The concept is there too, but here is more highlighted. So we divide, and with the primary, we deals in a way, with the secondary in another. For the parameters in the elements, I mentioned in beam, we have axial load, we have shear, we have bending, we have torsion. We divide them, say some of them are deformation control, and some of them are force control. And based on that, how much ductility they can provide after reaching to their strength. How much this A, for example, this B, on the deformation, how much classic deformation they can carry after reaching to yield without losing a strength, and after losing a strength, how much more they can with a residual strength they can carry. So very detailed, the numbers are here, but we divide. With deformation control, we deal in a way, with force control in another way. That's the approach here. We try to divide as much as possible to make our work as complex as possible, because it's engineering work, in the office work, is no problem. But the application of the retrofitting in the site, in a building that is working, is very difficult. That should be reduced. That cost and disruption should be cost. Very interesting, very interesting. We want to, here is, for example, concrete. This part is concrete. This is beam, the same concrete. But when we want to, and as I said, for calculation of capacities, usually in the existing building codes, we don't provide new formula. When we want to estimate the strength of the element on the shear, on the axial load, strength of the element, the capacity of the element, we use the same formula from ACR, from VMBC, from whichever code that we are familiar. But the material property that we put them is different. So this is a beam. We test it. They ask, what is the strength of concrete here? What is the strength of concrete here? We say, what do you want it for? Do you want it for calculation of the force control strength or a deformation control strength? It is the same material, but for the parameter that is sensitive for force control parameters, we use mean value minus 1 standard deviation. And for the deformation control parameters, for when we want to calculate, for example, the bending capacity of a beam, which is a deformation control, which is a ductile behavior. Deformation control is ductile behavior. We use mean values. And mean value is much more than minus 1 standard. You see the approach? This is the approach. Dividing the elements, dividing the responses, and a different approach with the ones that are critical, the ones that are less critical. The same approach. So, for example, we introduce the another parameter, ductility demand, for example. Now I can go faster to reach to the review part, but for the even for force control behavior, we make it for critical ones. We look deal in a way a modification factor for ordinary, for non-critical. So that's that. As we should finish around 10:30, and then there is a question and answer, and then it seems there is a test, something like that. So to be fair, for the test, usually there are some questions. So we do some review. Hopefully this review is correlated with the questions. So if we have a quick summary, what we covered, what the two category of design requirement of a building in earthquake-prone countries or regions. What are two design requirements? Is it, for example, cracks? Is it, for example, stiffness? Is it strength? Is it ductility? For the earthquake design is strength and ductility. Strength and ductility. And the main question of tonight, why seismic design codes cannot be used for assessment of existing buildings? Why? Because they don't have the needed requirement, the detailing of the according to new codes. So you can use those approach when they are have the same good detailing. When we say what is systematic evaluation, what systematic evaluation means? Systematic evaluation means that we should look at the different performance level, different seismic assumptions. Systematic is two. What was the main characteristic as primary elements? Primary elements, they are the elements that we rely on them to resist both seismic forces and deformation, seismic deformation. Deformation control function, what is the difference with force control? The deformation controls are more ductile. Force controls are the ones that are brittle. What that means, the different performance level. For example, life safety. What is that? You should feel damage level. For example, we say this much damage, this much damage, ductility means damage, this much damage is immediate occupancy. Life safety is more damage than, for example, immediate occupancy, is less damage than the collapse. So it's a sense of damage, the performance. Which one of the factors in base shear calculation of BMBC is not applicable to existing building? Of course, that's it. Calculation of capacities for deformation control and force control are different. Yes, that's the main approach. We want to make it complex. Even for the same material is here, but for the brittle behavior, use lower bound. For the behavior, bending, for example, you use more values. That one, lower bounds. Good. And why systematic assessment is complicated? It's not. We don't simplify it. Why we want it? We want it to be complicated. Why? Why not just use a R? Because for existing buildings, if you want to use one number, will be the lowest one. It becomes very uneconomical. It's very overestimated. So we don't want overestimation. We don't want overestimation in the our evaluation. What is the meaning of performance level? What is performance level? Performance level means damage. How much damage? The performance level means, more accurately, the acceptable damage for that level. So we have covered some very fundamental things. Generally, we know what is systematic retrofitting of existing building means. We know now that unfortunately, we need to the course for the existing buildings if we want to evaluate systematically an existing building, because the new buildings hides the complexity in a place that we don't have access to. That is in new building detailing. They can inspect the building and be sure that the construction goes according to details. But for existing building is gone. None of the detailing is there. Different response parameters. Some are force control, some are displacement control, some are brittle, some of the ductile, and the damage and performance are exactly the same thing. And why the modeling is main issue in the systematic assessment. In these 10, 15 years, the most important aspect and improvement was in modeling, because we want to model. It's not like the seismic design that we can use a R factor and finish it and go with the elastic analysis. We should model all the deficiencies that a building has and bring those deficiencies in modeling. And maybe a building has none of the requirement of the a new building code, but it still satisfy the performance level. But you should model all the deficiency and show that building with all these deficiency still can satisfy the performance level. So all the good things that happen in the systematic evaluation is in the modeling. Right. And I think with this, we can thank you for your patience. Yes. And if you have any questions, I'm sure Mr. Rando can help me how I can answer the questions or receive the questions.
Dr. Mogadam, can you hear me? Dr. Mogadam,
Sabura, Mr. Brown, yes.
can you hear me? Or I think you cannot hear me right now.
I don't have your voice. Just a moment. I think I should stop sharing. Let's see what happens. Oh, yes. That's it. Sorry, I was not be able to hear at that point, but now I hear it.
Oh, can you hear me now?
Yes, perfectly.
Okay,
Sorry
okay,
for
okay. No problem. Dr. Mogadam, this was a very, very good presentation actually. Like you went really through the basics, like right into the crux of the matter, and then came back and then went through the provisions for existing buildings and stuff. And that this was really well presented.
Very nice of you. Thank you very
It
much.
was a
It's nice of
very structured kind of a presentation that you did. So we have some questions, and in order to access the questions, if you go to the top of your screen, you should see, or you are not sharing your screen right now. So at the bottom of your screen, you should see a Q&A button. Do you see the Q&A button on your screen?
I try to find the okay Q and A at the bottom part.
Yeah. So if you click on that,
Yes. Yeah, I found.
yeah.
Okay.
If you click on that, you will see a bunch of questions that is there.
Okay, sure. So I go at the top and
Yeah.
start
Yeah.
looking at them.
Yeah. So
Uh,
So you drag it to the top, and I would recommend one thing that before answering the questions, just click on the question. Otherwise, it keeps on moving. So if you click on the question, it will stay on the
okay.
screen, basically.
Okay. Yeah, good point. Very good point. Yes, it was moving. Okay. So, if I'm not mistaken, the first one is some of our engineering colleagues are trying to
Oh, that
attend
I
to this.
answered
Oh,
already. Yeah.
okay. Well, yes, I saw. Thank you. Then, okay. Uh, the other one still is regarding the bridge, which is very important. Then,
I think the first question is
okay.
relevant question is what is the basic features? What is the basic features which will be more important for existing buildings? That is the first relevant question. I think just answer the
Yes.
questions that are relevant to your presentation, Professor
Okay,
Mogadam.
now it's a very nice question. In fact, what is the basic features which will be more important for existing building to be demolished or not in point of view of seismic vulnerability buildings? There are a couple important features which are dealing mainly with the preparation of a good model. So our most difficult part is how to model a building, how confirmation good and reliable model. But the real focus of question is not on that part, is on the decision at the end. Usually a very simple approach that is worldwide is being used is a cost benefit analysis. Usually they do the calculation of the different retrofitting schemes, the cost for the retrofitting to bring this deficient building to the that performance level that is expected or wanted from that building. What is the cost? uh, you try different schemes and you come up with the least cost, and then compare it with the demolishing and rebuilding a new building in place of that. And then the ratio between retrofitting costs to the rebuilding, this ratio usually governs in decisions. And worldwide, they use between zero point 0.3 to zero point 0.4 as a starting. And because there are other issues too, sometimes this building has some historical importance. You want to retrofit it with any cost. Sometimes is, for example, is a school in the only school in this area. So you want to retrofit it with a little bit more than the usual cost. But 0.3 to 0.4 is widely accepted in this decision. Then another dear colleague asked, what is the difference between life safety and collapse prevention? So in life safety, we expect that no death happens. But in collapse prevention, usually a number of people get hurt and a number of people get killed, but the building doesn't come down, and the floors doesn't crush the whole story together. So the stability is there, but you can't guarantee the life safety. But life safety, you can expect least number of the fatalities. Then another dear colleague asked, if seismic design code cannot be used for assessment of existing building, then what seismic force should we use? Very good question. A starting point for tomorrow. Tomorrow, we are working on linear approach, and starting the main item that we will discuss is calculation of the base shear for the existing building. Didn't understand this portion. You are every right to say that, because I just show a formula and pass that. But tomorrow, hopefully, we will have more emphasize about that. So we keep your question. If tomorrow still you didn't get the answer, we will discuss that. Is there any difference in the base shear force for assessment of existing building compared to the new building design? Yes, in the new building design, we as the base shear that we use is we reduce it for the whole building by dividing that by a factor R. But here, we don't reduce, as we will see again tomorrow. And a little bit the way that we calculate it is easier than the general approach is the same. We go through the response spectrum, we need the weight of the building, and second law of Newton, and the same approach, but it's a little simpler. And there is a fundamental difference too that, let me explain that tomorrow. Can we use R value determined from pushover analysis in assessment of existing buildings? Yeah, sure, but most probably the owners never give you another job, because it becomes very costly. You find the R value, very small R value for the building, and then you assume that all the elements of this building, the capacity, the ductility capacity that they have is related to this value. But there are some elements are much better. This is really representative of the worst case elements. So you come up with a costly retrofitting scheme, and then nobody goes for retrofitting. So please don't do that. For an existing building, satisfying OMRF detailing and the building exists in mandatory IMRF zone, can we analyze this building for higher base shear by using lower R values? It's a good engineering approach, a general and engineering approach that so if there is a difference in detailing, we compensate that is basic. So that's the idea. But doing that by ourselves is not is a little most probably the authorities don't accept your judgment on the values. But here in the code for existing buildings, the tables provide a very good tool for doing this. But again, if those authorities let you to use the code for existing buildings for new buildings, because usually they said a building will not get it, the permit and still is not constructed, is not assumed as a new, is still assumed as a new building, and the binary approach should apply. Should be either all the detailings are applied, all the code procedure is applied or not. But otherwise, from the theoretical point of view, your approach is very, very good. Okay, thank you very much. A couple of our dear colleagues, they said that my voice was, they can hear at that time, but unfortunately at that time I didn't know that I could check in Q&A. Tomorrow I will use that. Thank you very much. Now, what is the difference between life safety and collapse prevention? Doesn't collapse prevention automatically ensure life safety? In fact, life safety ensure collapse prevention because life safety is less damage, collapse prevention is more damage. So if we limit the building's damage to life safety, the collapse prevention requirements should be, a dangerous question that I missed about break. So sorry for that. Excellent. Oh, thank you very much, dears. As we cannot model the rebar detailing in the commercial software like ECPS, does the pushover analysis from these softwares give us the correct ductile behavior and plastic hinge results? Always it's good to do some kind of verification, but they are not bad because they have usually some other tools like section designer, section builders that provide the behavior care for the sections and for the elements. So generally should be okay, but it's always, in fact, in some projects they ask that you do some kind of verification. What is mean return period? I don't know why when I use mean for return period. I don't know really when I use this word, but the return period itself is a way that we show the level of earthquake, and it's exactly correspond to the probability of occurrence of the earthquake. So 475 return period is equivalent to 10% exceedance in 50 years. But the mean return value, sorry, I don't know when I use. Would you please clear seismic hazard level 20%? It depends on the situation. We can have from return period 1 year return period to 1,000 years return period. The different codes they change somehow the values. For example, in recent versions of ASC 41, they they try not to use exact values for the return periods for the new buildings for the existing buildings, which is logical. Anyhow, the existing buildings, we don't expect to usually to bring them to the same level that a new building right now is built. We can bring them to, for example, 90% of that, which much more saving. 80% is much more saving. So because of that, every now and then in the projects and in the codes, you can see that instead of, for example, usually we used to 2% to 50 years and 10% to 50 years. But sometimes for example, for the pipe design, you see that return period of 75 years they use. For example, some other platforms, for example, in the sea, they use different return periods. So is a decision either by code or by the client. Yes, a good reference book is the ASC 41 itself and the commentary of it, and many publications by FEMA and other agencies, both in US and others. If you search for the existing buildings in ATC, in FEMA, they have in the publication part, they have, and also the examples. You can find example books as how they implement that for different buildings. When the building cannot be retrofitted, what we can do usually is the best is to demolish it, because because anyhow it's dangerous. Sometimes in some government agencies and even private firm, they change the function of the building. For example, it was a very important building for them. They change it to a place for use it as a just depositing and saving material. So sometimes is and because of your question, I remember answer to another question that a friend before had, that I said that usually the threshold are 0.3 or 0.4 for the retrofitting is being used, but sometimes even the retrofitting cost is more, but you try to retrofit the building, because if the regulation of municipality is changed, and if you, for example, demolish the building, then you should for example, 3 meters the weight of the length of the building, for example, should be reduced according to new area plan. Therefore, it's better they try to retrofit it, because not to use their area of their building. But otherwise, generally, the first things that they consider is the rebuilding, because then they can make it sometimes the number of floors much more, and a new building, and finding the interested people to buy is easier. Is all people, organizations in Bangladesh will accept the adoption of foreign code for evaluation of existing building through I believe it is not possible, cost effective to evaluate an existing building in new BMBs. Very, very nice and important question, because usually foreign codes foreign for example, data maybe is not directly possible to be used in another country. But many of them, in fact, can be used. It's like medicines that we are using. The medicine that is used, for example, for cold, is the approach in, if you are Bangladeshi or, for example, US citizen or European, is almost the same. Although that are many habits and things are different, and many data, many of the work that in these codes are just the format, the framework. For example, you want to use one of the tables regarding the modeling of this element. So when you want to model this behavior of this element nonlinear curve of the force deformation of this element, it gives you the format. But the strength of that point is dependent on your concrete. So if your concrete here in this city is better than that, it becomes, then the capacity of the those, for example, say ductility capacity of that is depend on few items. What is the ductility of section? What is the confinement of the section? And what is the shear in the section? So if the confinement here is worse than there, the curve will be different. So many of changes in different countries, many of changes in different places within a country, they are directly changes the, because it gives you the formula, it gives you the shape of those elements, but the values comes from the test that you are doing there. Then, okay, oh, I forgot the advice of dear Mr. Ruda, and then I lost the question. Now I came back. I should click. Okay. What is the basic concept of seismic evaluation in existing building? What is the basic concept of seismic evaluation in existing building? The basic concept really is, first I remind that there are different approaches for assessment, and we have very simple approaches, as I mentioned, with using fragility curve, then using the rapid visual screening, then using, for example, more enhanced simple calculation, then going to the detail. So generally, we expect that if you start from the simpler ones, your results be more conservative. So usually we try to do that. With the, for example, quick screening, we got that this many buildings are safe, these are vulnerable. Then on those vulnerables, we do a more detailed analysis. Then some of them comes safe, less number comes vulnerable. So as you use more sophisticated, more time-consuming approach, it gives you more exact values, and simpler one are more conservative. So simple approach sometimes identify building as vulnerable, which with the more sophisticated approach, time-consuming approach, you pay for more engineering work, but you get at the end, because there maybe your building doesn't need retrofitting or much less retrofitting that the simpler approach. Yes. So general concept of seismic evaluation is that we want to, for the existing building, see that at different level of earthquake, what level of performance is satisfied by this building. And then the owner, then the society, then the authority can decide that this is good, or they want to enhance that, needs retrofit. But give a overview of the existing situation of this building, and how we give that overview by giving the performance level that this building can satisfy in different level of earthquakes, and then we say that is good or not. Okay, it seems that that was the last question. Is that true, Mr. Rudra?
Yes, Professor Mogadam. Um, so yeah, I think this is a good point to end the session today, and I will turn on the quiz for people for that attendees. Um, to They can go to the portal and attend the quiz.
Okay.
Thanks, Professor Mogadam, and we'll see you tomorrow again with the second lecture on existing buildings. And yeah, so you can join the same time at around 7:45 probably, and we'll do a
Okay.
quick sound check and
Thank
continue.
you very much, Mr. Rudra. Very
Yeah,
nice coordination. Thank you very much.
yeah. Thank you.
And
Thank you so much.
thank you, dear colleagues, for attending. Good night.
Good night. Good night, Professor Mogadam.